Okay, so time to get started. Here's what we were talking about last time. We spent a bunch of time talking about graphs as a specific, construction. This is a specific process by which we can take a function, algebraic object called a function, and by way of this specific arbitrary, let's note, process, we can create a picture. Right? So it's a process that turns a function into a picture. And this details matter, right? So the idea is that for any given input, there is a corresponding output, and you smash all of those numbers into a single ordered n plus 1 tuple, we call it, representing thus a point in the case of this example that I've drawn here, a point in R3. So the weird thing about a graph, this function that we're looking at an example of, the domain is R2, the target is R1, 2 and 1, and yet the graph lives inside of R3. Right, so the input and output variables all together. It's really a kind of a weird construction if you think about it. Right? Okay, so there's that. But then there's also this other construction, the level set construction. Right? This is a different construction where instead of setting the function equal to a new variable, instead, to take a level set, we set the function equal to a constant. It gives a different equation for which we get a different picture. And I don't want to go through all the details again. We talked about all this last time. There is, of course, a connection between level sets and graphs, and this example here illustrates that pretty nicely, I think. Here's the graph of this function. That same function, here's a level set, or some level set of that function. Same function in purple. Right? You see the two different constructions. Level set means set it equal to a constant. Graph means set it equal to a new variable. You get different equations, therefore different pictures. But the connection, very nice connection between them, is that cross sections of the graph correspond very nicely to level sets. So, something to think about. Okay. All right. Now, moving along, I think these are fantastic examples here. Look through my old midterm exams to see lots of old midterm exam questions that are morally equivalent to these examples. Again, don't underestimate. Don't look at this and think, I could do that algebra in middle school. Right? And then underestimate the point of these questions, which is to properly and strictly interpret the terminology and make proper sense out of what we're talking about. And the algebra, of course, is trivial. Yeah, of course. We ended with this example. Every graph can be interpreted as a level set of a different function. And there's this wonderful little trick here. This little move, you see, those are morally equivalent equations. And each implies the other, so you have exactly the same solution sets. One of them, though, looks like a graph of something, and with the other one of them looks like you're taking a level set of something. Different functions, though. You're taking the graph of this thing over here. You're taking a level set of a visibly, obviously different function. Okay, so just as by way of example, suppose you're looking at, let me zoom back in here. Suppose you're looking at this function right here. That function, its graph, is given by that equation. Right? Take the value of the function, set it equal to a new variable. So that's what the graph's equation looks like. Note that equation is totally equivalent to that equation, which represents, you'll notice, a level set. A level set of this other function. Sorry, I wanted to switch colors there. Here we go. This other function. Okay. Yeah.
thought that level set would be in a different dimension in the graph.
No, the level set. So these are two different functions. So it is confusing because if you take one function, the graph lives in one world, level sets live in a different world. You're right. So we're kind of doing the other way. We're looking at one picture and we're saying, well, that's a level set of one function, and it's a graph of a different function. So two functions that by different constructions give us the same picture, instead of previously we were talking about one function which by different construction gives us two different pictures. So we're kind of coming at it, you might say, backwards in this case. Yeah. So this level set of G, this graph of F, are exactly the same things. They're both this same surface, this familiar surface that we talked about, a long time ago. This is a paraboloid in R3. Right. Okay. Thinking of it though as a graph has certain geometric interpretations when we get to calculus that we'll talk about later, and likewise, thinking of this exact same thing as a level set of something else has different, also very valuable interpretations when it comes to the calculus. And we'll again talk about that later. So very quickly, let me note that even though every graph is a level set, not every level set is a graph. Easy example. Here is a level set. Right, this equation here, it's a circle. That's a level set of a certain function. Right? It's not the graph of anything. It just isn't, right? Fails vertical line test. Whichever way you go, not a graph. All right, so this is a one-way trick. You can turn graphs into level sets, but not the other way around. A couple of it, I like to make the pitch for why people should care about level sets. I mean, a lot of it's going to come from calculus we haven't talked about yet, so some of the pitch is going to have to wait. But a couple of easy observations I can make right now. This dimensionally simpler thing I think is very persuasive. We've already kind of talked about this a little bit when we talked about the preposterousness of going hiking and carrying around a three-dimensional model of the mountain that you're climbing on. That's ridiculous, right? And trying to understand a weather report by looking at a three-dimensional model of the temperature function. It doesn't make any sense at all. So just another example of the same thing. This function, the level sets are super easy to draw. I mean, you can't draw all of them, but you can draw a representative sample, and you get a really good geometric understanding of what this function is doing in some sense from that picture. And the graph is nice in a way, but a couple of bad things about this picture are first of all, it's really hard to draw. And second of all, even having drawn it, it's not clear. I mean, I seem to be suggesting that I have kind of an angled trough here, but based on the picture alone, how is that trough exactly is it going in the direction of the y-axis, or, it's poor art, and so, you can almost kind of see maybe that's coming out toward the first quadrant of the xy plane, or something. It's hard to see from the picture. Whereas, in this picture, very clear, the axis of symmetry is the y-axis. So, arguably, the level set is not only an easier picture to draw in a pretty significant way, it is a better picture. So, for your consideration. For those of you who are still holding out, I'm always going to think of it in terms of graphs. This next example, the dimensional simplification is key. If you try to draw level sets of this function, well, level sets, you take this function of three variables, you say you get the various constants, you get various equations of three variables, kind of hard pictures to draw, etc. And you look at these, they're ellipsoids, right? But what would the graph of this thing look like? There's three input variables, one output variable. That means you're going to have an equation of four variables, and you're going to have to try to draw a four-dimensional picture, and you will fail. Because we don't have four-dimensional paper. And we can't fake it even on two-dimensional paper. So it's just not going to happen. All right. So, by the way, this is not at all weird to have a function with a mere three input variables. Not weird at all. So you cannot just rely on graphs. Okay, we're going to have to understand things from a level set point of view as well. Okay, so enough of that. New topic now. We're going to get into limits. Right, so y'all remember limits from single variable calculus. It's really important. I like to make the observation that limits are really the most fundamental idea in calculus. Right? A lot of people would say it's derivatives. A few people might say integrals. These are the big ideas of calculus, derivatives and integrals, right? But if you look at the definitions, it's a definition of a derivative. This comes from a limit. What's a definition of an integral? It comes from a limit, right? So this idea of limits is really the foundational idea of calculus. So it's kind of a big deal. So a quick reminder. Now, by the way, there is a formal definition of limits. We're not going to talk about that in this class. Not because it isn't important. It's very important. It's a little bit beyond. It's not quite what we're here for in this course. If you are interested in seeing a more serious presentation of the strict official definition of a multivariable limit, you can take a class like Math 431, and some books will even talk about it in a context like this, but usually don't emphasize it. So, anyway, so here's the idea. Here's the way you think about limits. I'm going to start with a single variable point of view. Here's our familiar x-axis on which we do business in single variable calculus. And the idea is, as you approach A from the left, and you're keeping track of how the values of the function's changing, you can talk about what we call the left-hand limit, right? And as you approach A, on the other hand, from the right, keeping track of the values of the function, you can get the idea of what we call a right-hand limit. And one point of view on what a single variable limit is what is the value if there exists a value that equals both of these? In other words, are these two limits equal? And if so, then that's the limit. Yeah. And if these are different, then there is no limit. Limit doesn't exist. It's garbage. Okay, so this is what we're going to go off of to motivate a multivariable limit. Now, instead of having a single independent variable, thus the name single variable calculus, right? If we now have multiple input variables. So notice here, by the way, I'm not drawing graphs, I'm not drawing level sets, I'm just drawing the domain. This is just the inputs. So you might even say that, this being the domain, that the function is like this. Right, we've got a domain, we've got a target, like that. I'm just drawing pictures in just the domain. The output values are not on this picture. Okay. The idea is that as we approach some point in the domain along one path, along a different path, note, I'm allowed to curve, right, along whatever path, however many paths, and this is the sticky point of multivariable limits. So many different paths. Along all of these different paths as you approach that one point. All of these individual path limits have to be equal to each other. They all have to exist, and they all have to equal to each other. Okay. All right. Now, I know that this isn't the picture that y'all are accustomed to seeing when you're talking about multivariable limits. Single variable limits. And, of course, the reason why is that y'all saw single variable limits in a single variable calculus class in which everyone always draws graphs. Right? I didn't want to draw a graph to start off with because I'm trying to pull y'all away from this reliance on and assumption that everything you ever see is a graph. Right? So I wanted to give you this different picture first, but having done that, let's look back at graphs. Here's the familiar picture of what a single variable limit looks like. The idea is that as we approach from the left, we're keeping track of the values of the function. As we approach that point, we get some value. And as we approach from the other side, keeping track of the values of the function. And the limit is that shared value. So if as you approach from the left, the function is approaching one number, if as you approach from the right, it's approaching, the same number, then that number is the limit. So let's see what this picture would look like. This kind of a picture in the multivariable context, and it's hard to draw, which is why we usually don't. Right? So here's the same idea in a multivariable context. Here's a graph of a function, f, from R2 to R1, right? 2 input variables, 1 output variable. So you can see we're looking at a graph. As we approach along one curve, the values of the function are approaching some value. And as you approach along a different curve, the values of the function are approaching, again, hopefully the same value, and no matter what path you approach along, artistic challenge. Along all of those different paths, we need to make sure that the value of the function on these paths is all approaching the same value. Okay, so now before we go on and start doing calculations, let me just take this as evidence of why we don't usually draw the graph picture in a multivariable context. It's too hard, right? That's a tough draw, and plus it's not like I'm using the picture of the graph surface here to draw some conclusion. The picture. What did I draw on this picture? There's a bunch of empty, just the whiteness of the page around the point I'm interested in. I can't actually draw what's really going on around there because I have a one-dimensional pencil line with which I'm trying to draw a two-dimensional thing. It's a mismatch. It's a loser from the get-go. So the pictures just aren't that useful in this context. What we need to keep track of when we're talking about multivariable limits is what are all the different paths that I've looked at, and what then I have to do calculations on those paths. But that's where the action is. It's down here. Right? So that's why we will typically draw just the domain. I'm not going to draw the graph. Why would I draw the graph? It's just artistic inconvenience that doesn't really serve the purpose. Okay, so heads up, all the pictures that you're going to see, most of the pictures that you're going to see anyway, henceforth will not be graphs. They'll just be pictures in the domain. So for example, here's a multivariable function of two variables, x and y. Suppose I'm interested in computing its limit as x approaches the origin. So I'm interested in that point that we're approaching. And now, let's do our first calculation. How would I approach that point? Well, my gosh, there's a bazillion different ways in which I might approach that point. But let's start with an easy one. Let's approach along the x-axis. By the way, notice that along the x-axis, y is equal to 0. That's convenient. Y is equal to 0. And by the way, I emphasize, I am not saying that as we are moving along the x-axis that y is approaching 0. No. Y is flat 0 everywhere along this path. X is approaching 0. Y is 0. Right? Does everybody see the difference? Okay, so y is 0, and so I'm going to take that and plug it into there, thus turning my expression into this. All right, here's that y. Colors again. Here's that y equals 0. X is approaching 0. Color choices. X is approaching 0. So I no longer have to say multivariable limit as this vector approaches that vector, right? I can just say, well, the x coordinate just needs to approach 0. get to this code. And I find myself back in familiar territory of single variable calculus. This is a Calc 1 single variable limit, right? And you just compute that limit by usual means. And conveniently, of course, the algebra on this one works out really nicely. X times 0 is equal to 0. I don't really care what X is or what it's doing. Anything times 0 is 0. And so this expression turns into, well, it's 0, right? 0 divided by X squared. And the limit of 0 is, of course, 0. There's a couple of tricky things about this calculation. I do want to remind y'all of, how single variable limits work. A lot of y'all might have had, I don't know, look, if you have AP credit for single variable calculus, then you have a high school presentation of limits. And a lot of those are bad. I know because I had one, right? And my school wasn't even that bad. So, one quickie, and I'll come back. There's a couple of potential pitfalls in this calculation right here. The first one I want to point out is some people would look at that and say, but isn't that 0 over 0? Because X is approaching 0 too. Nope. This is not 0 divided by 0. One of the very important things about limits is that when you say X is approaching 0, the whole purpose of limits is to absolve ourselves of the responsibility for whatever catastrophes might be happening when X is actually 0. Right? I mean, that's the whole point of limits, is that we are no longer responsible for what happens when X equals 0. Now, said differently, if X is approaching 0, that means that you may assume, for the purposes of your calculation, that X is never 0. Right? So this is not 0 divided by 0. This is explicitly 0 divided by never 0. And that is 0. All right, so anyway, make sure you're clear on this point about, what is a single variable limit and what can you conclude about the things that's happening with, the thing that's approaching the whatever is never equal to that whatever. Okay. All right, there's another thing I want to talk about in this, but I want to come back to it in a minute. So what have we done? We have decided that we wanted to move along this path, and along that path, the limit is that value. What do we conclude from this? Nothing. I've computed one path. For the multivariable limit to exist, I have to approach along every path. Okay. Let's do the next possible path. Let's think about along that line, y equals mx. Which, by the way, also is going to do the calculation in the other direction as well, but whatever. Okay. So, for along this path, or you might say along these two different paths, let's do that calculation. By the way, in fact, it's really more than just those two paths, because notice, I didn't say what m is. And once I do this calculation and get some answer, we'll worry about the details in a moment, that answer will be a function of m. That will tell me what happens along every such line. So this will actually tell me all at once the answers for every path, every straight line path that I might take to the origin. Okay, now we're talking. All right. Pretty persuasive. This is an important calculation. But anyway, let's just think of one at a time. So, along that path, well, how do I keep track of what's happening along that path? I'm a big believer in the following. Parameterize that path. It's easy to do. X comma mx. Right? This is that graph parameterization that we talked about previously. Let x equal to whatever it is, and then y is what it has to be based on whatever the equation is. It's a real neat trick for parameterizing curves. Take that, plug it in. Notice that there's your x and there's your y. I'm just plugging in the parameterization. Likewise, again down here, that's x and that's y. So I'm just plugging in my parameterization and do another single variable limit. Notice that the x's all cancel here, and this is not a function of x at all. It's independent of it. X can go to 0, it can go to wherever it wants to go. I don't really care. That's this value. Okay, so that's another calculation, and we see that along this path, we get that answer. Okay, now what do we know? We haven't checked every path, but we've checked a lot of paths. But remember, here's a big point. For limits to exist, we need all of these different answers that I get along all of these different paths all to give us the same value. And if any two are different, the limit doesn't exist. Right? If you approach in the domain along two different paths and the values are, along these two different paths, you get these two different limits, there's some sort of a, you're going to want to call it a jump discontinuity, right? You remember in single variable calculus, jump discontinuities? It feels a lot like that. It could be, by the way, much worse than a jump discontinuity. There's the categorization of different kinds of limit failures is exotic. There's all sorts of weird things that can happen. So anyway, but the point is, clearly, swing and a miss, limit doesn't exist. And that's what we found here in this example we were just looking at. Right, we've gotten two different answers along two different paths. In fact, come to think of it, I don't even really need this one. I can throw that one away. I've got bazillions of different answers along bazillions of different paths just in this one calculation. Take different values of m. That's having you approach along different lines, and this function here, this expression, will take different values for different values of m. So, done. This limit doesn't exist. It's not always the same value. So, for example, plug in m equals 1. We get 1/2. That's not equal to the value that we would have gotten if we plugged in m equals 0. So this is garbage. Yeah.
So is there an infinite number of paths to approach that by?
Yep.
You can just be curving it form.
Yeah.
It only takes one for it to not exist. How
Yep.
do you prove that it does exist?
In this case, it does not exist. You mean in some other... Yeah, and that's a great question. We'll get to that. There are a couple answers to that question, but we're not quite there yet. Yeah. Okay, so, yeah.
In this case, the x squared cancels out. What if the bottom is like x squared?
Yeah, it'd be a harder problem, wouldn't it? Yeah, we'll have to worry about that. Totally. Yeah. Yeah, so this is just one example. Right? And we'll get to other examples in a minute. By the way, let me go ahead and confess, the punchline of this conversation is not going to be that I will give you, here is the algorithm, take your question, put it in there, turn the crank 4 times, and out comes your answer. That is not how this is going to work, unfortunately. There will be some questions to which the methods I will show you. I didn't set that sentence up right. There are some examples for which the methods I will show you will not work. Good news, those won't be on the test. Right? I'm not going to give you anything unfair. Right? I'm not going to ask you to answer a question for which I haven't given you the proper tools. But we're simply not going to present a complete, exhaustive set of tools that address all such questions. So, y'all brought up some very worrisome issues that might arise, and some of those we'll be able to address and some we won't. Okay. All right. Here's another example. No, I've got ahead of myself. I wanted to come back and talk about this single variable limit up here. Another thing that students do wrong sometimes. Some students will not even get to that in the first place. A lot of students will write down equals fraction limit of x times 0 over limit of x squared plus 0 squared. And individually, both of those limits are indeed 0. And then get this. And what's wrong with that calculation? Anybody remember? It's pretty tempting, right? Limit of a fraction is a fraction of the limits. We all remember that theorem. This limit's clearly 0, that limit's clearly 0. 0 over 0, of course, is not defined. So what did I do wrong? Or is this right? Is this okay? Yeah.
Well, if you're taking the limit, it's never actually going to equal 0, so x squared would be
Now, limits actually equal certain values. So let me go ahead and point out what the problem isn't. This actually is, that is indeed equal to 0. Yeah, and this here is indeed equal to 0. That's not the problem. The problem, which I deliberately glossed over for dramatic effect, the problem is what I wrote down here. Get rid of those check marks. Where I asserted that the limit of a fraction is the fraction of individual limits. That's not true as a general fact. It is true often. It is true with conditions that have to be checked and which are not satisfied here. So the conditions, if you want to write down a limit of a fraction equals a fraction of limits, the numerator limit has to exist. That's non-negotiable. The denominator limit has to exist. So that's the second rule. That's non-negotiable. And the third condition is the denominator limit cannot equal to 0. If it is, then this, as it is in this case, then that's just false in the first place. Yeah? Everybody good with that? Hopefully a flashback to single variable calculus. And by the way, this is a great example of why mathematicians are so uptight about rigor. Is because if you aren't careful, if you're not uptight about rigor, then very often you can end up writing stuff down. It's complete nonsense, garbage, wrong, right? And it's I got to give you this warning. I mean, this is a class about deductive reasoning. It's a class about proper, reasoning. And if you were to write this down on an exam, you write this down first, and then you write that, and then you write 0 over 0 and claim, therefore, the limit doesn't exist. That's not going to get much, if any, partial credit. And I emphasize the fact that you got an answer which happens to be pretty much the same as the answer that we ended up with, that is coincidental and irrelevant. All right? It's not about answers, it's about reasoning. All right? So, the right, thing in the box at the bottom of the page, not the point. Okay. All right. Okay, here's another example. Having noted the pointlessness of checking along the x-axis alone, we can do all lines, practically all straight lines. Technically, this doesn't get the y-axis, but we can do the vast majority of lines toward the origin with this one parameterization. Again, notice that we parameterize in the same way. There's x, there's y, et cetera, et cetera. Limit. Lots of the x's cancel, and I end up with this. And as x approaches 0, this is x times a constant. That limit is indeed 0. Okay. So here's what I have shown at this point. I have shown that along every straight line, said differently, from every direction along which I might approach the origin, every possible direction, I always get 0. And there's going to be a temptation. You're going to feel this urge to say, therefore the limit is 0. That is not true. It's not legitimate reasoning, because the thing is, we've only checked the straight lines. Look back at the picture here of, here's what we have to do, right? We've got to check not just the straight lines, we've got to check the spirals, we've got to check the whatever that is, right? Parabolas, cubics, quartics, squiggles. Squiggles are hard. You got to check those squiggles. Right? So you checked the straight lines, have you? That doesn't mean anything. It doesn't allow you to conclude anything at all. So don't step on that landmine. It's a nasty little landmine. Lots of students will get this 0 and say, hey, that's 0 from every direction, therefore the limit's 0, check mark, smiley face, done, and walk away and not get hardly any partial credit for the problem. Heads up. with that. Okay, so what else can I do along the lines? I've got 0. Okay, so let's try along curves. Let's try along parabolas. And again, there's a single variable limit there. I've already given you all plenty of warning about how, look, you got to make sure that you can do these kinds of calculations. Let's focus on the multivariable. So I'm warning you about making sure that you're, freshened up on the single variable. I'm going to leave that to y'all now, and we're going to talk about multivariable here on out. So along the parabolas, I get 0 as well. All right, and now we're starting to feel a little bit more confident. I've tried straight lines and a very large category of curves. I keep getting 0. What does this prove? Nothing. I haven't checked the squiggles yet. Right? You haven't checked the squiggles, you haven't checked all the curves, and it's got to be checked along all possible curves. So this proves nothing. Yeah.
Didn't you just say you can't put the limit on the fraction of the limit is not good? So
do what now?
You can't just take the limit of fx over gx and then equals the fx limit of fx over limit of gx.
Nope, because those limits don't exist. Right, so I just talked about that, right? So if you look at this original thing here, we have limit of a numerator divided by limit of a numerator divided by denominator. If you want to assert that that's equal to the ratio of individual limits, then both of those individual limits have to exist, which they do, and the denominator limit can't be 0, but it is. Right, the limit of this denominator is 0. So you can't do that. That's absolutely false. And again, if you do that on an exam, can I emphasize, by the way, I want nothing more than to give y'all points. Right? That's my favorite thing to do, is to write a big check and full credit when I'm grading a paper. But I can't sometimes. So help me. Right? So if you do that on an exam, so I'd have to give you a 0 if you did that. Yeah. Okay, because it's not true. Okay, so these two calculations together, they don't show squat. I haven't checked the squiggles yet, and what else am I going to? By the way, am I actually suggesting that you should just keep trying higher and higher powers of x, and then check squiggles, and then check spirals, and then no. There are other ways. We'll talk about that in a second, right? But the fact that in this case, I've only checked a finite list of curves doesn't mean anything. Okay. So nothing so far. Okay. Just so you won't think that we're being pointlessly uptight, I'd like to show you all this example. So look at this limit here. Not even all that scary looking of a limit. I mean, there's a 7th power in the denominator, but whatever. It's just algebra, right? It's just there's no scary functions on here. So I'm going to leave some details for you all to check for yourselves. But if you check along all straight line paths, you will get 0. If you check along all of these parabolic paths, you will get 0. So why do I urge you not to spike the football too soon and celebrate? Oh, come on. How could it? Look at all the curves we checked. What are the odds? Right? Okay. So beware. If you check along the cubics, you do not get 0. And I think these are both, I think all of these are healthy exercises to go through and make sure you can responsibly, properly compute all those single variable limits, right? Because if you can't do the single variable limits, then you can't do any of these calculations reliably enough to get the believable answers. So make sure you can do those single variable limits. But in this case, we do get different values along the cubics. For crying out, it's so weird. It's very counterintuitive that this would happen. This is the kind of creepy that can happen in a multivariable context. So that's why we don't spike the football right there. Okay. Okay, so to the question that's been asked a couple times now then, how can I ever show a limit actually does exist? I'm going to show you all how to check the squiggles. This is a really neat trick. Tragically, this only works sometimes, but in those cases it hammers the problem, and that is to switch into polar coordinates. By the way, if you haven't seen polar coordinates, we will talk about that later in the course, not right this second. There's a lot to say about polar coordinates. We're going to do a lot of things with polar coordinates. Right now, I just need a very little bit, which is to point out that if you have some point, no pun intended, that point has what we call rectangular coordinates, x and y. Right, and it also has what we call polar coordinates, namely r and theta. Coordinates being just, different ways to describe where you are. So if you tell me the x and y, that tells me where you are. Right? If you tell me the theta and the r, that tells me where you are. So it's just called a different coordinate system. So polar coordinates, they call it. And we'll say more about it later. But here's some, on the basis of that picture, here are some true facts relating polar coordinates and rectangular coordinates. And this is really all we need at this moment for polar coordinates to be able to make great use of it. And let me show you an example of how useful this can be for multivariable limits. Consider this multivariable limit right here. By the way, that's the one we got stumped on a couple pages back. We tried the straight line paths. We tried the quadratic paths. We kept getting the same answer of 0. We know that doesn't allow us to conclude anything. We know that there are these landmine, weirdo, crazy catastrophes that can come up unpredictably late in the calculations, no matter how many individual categories of curves you mess with. So we know we have to check every possible curve, and yet we can't get there. What do we do with this question? So here's the lovely idea. Every single path approaching the origin has the feature that the polar coordinate r approaches 0, and furthermore, every possible path in which r approaches 0, the point is approaching the origin. So, specifically because we're talking about the origin, it's got to be the origin, unfortunately. Right? It's the only point that is uniquely characterized by just one coordinate. I don't need to know what theta is. If I know r is 0, I know where I am. Right, so it's a peculiarity of the origin. But the fact that unique fact about the origin means that I can switch a multivariable limit of rectangular coordinates into a single variable limit in polar coordinates. That's a cool trick. Right? And then everything else is just a matter of plugging in. X is r cosine theta. That's on the previous page. Y is, here, let me do it like this. Y is r sine theta, and also on the previous page is x squared plus y squared is r squared. The old Pythagorean formula. So I've turned a multivariable limit into a single variable limit, and those I sometimes can compute, right? And of course, sometimes it's hard. You look at this and you think, nasty, right? What are we going to do about that? Good news. It does, in this case, work out. Algebraically, that simplifies to this. Make sure you can do that. That's a nasty expression, but among other nice things, it is a bounded expression. So this is never, ever, ever, under any circumstances, bigger than 2 or smaller than minus 2. Bounded. Right? And this here is going to 0. So what happens if you have something that's bounded, never gets that big, and you multiply it by something that's approaching 0 incessantly? Well, then limits equal to 0. So what we have done here, let me remind you, we had this multivariable limit. We're responsible for checking all possible curves, not just the straight lines. Parabolas too, and don't stop there. Cubics, quartics, quintics, squiggles, the whole list, right, of different curves, and I've actually done that now. Because for every possible curve that approaches the origin, r is approaching 0, and in all such cases as r approaches 0, I get 0. We've checked all the curves. Now I emphasize that this will not apply to every possible problem. You do have to be approaching the origin. I cannot emphasize that enough in order to be able to make this connection to a single variable limit. Yep.
Can you transform stuff to move the origin?
Yeah, sure. You can. You can do a change of variables, and that's fine. But then you're going to end up. You got to do that in the expression that you're taking a limit of as well, and so you might end up making it nasty. Another thing along those lines, another thing that you got to worry about is we only were able to view this as a product because the denominator canceled. The denominator only canceled because the denominator simplified. So you really need a denominator that's going to simplify in polar coordinates. And if you mess with it, who knows, it might not. Right? So, I mean, give it a shot. Maybe, right? But it might not.
So it's like +1 or something.
I'm just saying that's where the landmine is, and there's all sorts of scenarios. But so there's that, and don't forget as well, it is very important to have an argument that you can address. You can't just say, "Oh, this is approaching 0, so I don't care what this is." If this isn't bounded, you've got no argument, right? Because what if it was r times 1 over theta? Uh-oh. What if theta is approaching 0? Just pick a path where theta approaches. Now you've got a problem. Right? So this has got to be bounded. And sines and cosines are nasty in a lot of ways, but they are bounded. And this combination of them is bounded. All right, so it's a delicate argument. But in some cases, it crushes the problem. Here's it working the other direction. This expression here, I'll leave the algebra to you guys, but that will rewrite like this in the polar coordinates. What can I say about that expression? Well, nothing multiplying it by 0. This is going to take different values along different paths. If you approach along one path where theta is one value, then this is some number, whatever it is. Come along a different path, the different value of theta, you're going to get a different value of this expression. It doesn't matter what r is doing. Right? So what this shows is that the limit doesn't exist. Different values along different paths. Okay. Last thing I want to talk about is continuity. Hopefully you all remember the definition of continuity from single variable calculus. We use practically identical definition in multivariable calculus. For a function to be continuous, the function has to exist at that point, the limit has to exist at that point, and those two things have to be equal to each other. Hypothetically, if you were to know that a function's continuous, hypothetical game, let's pretend. Suppose I know free information from on high that a function is continuous, then this formula right here is not so much a requirement as it is a tool. Because it says, hey, you want to compute the limit of this function? There's your formula. So a lot of y'all might have seen this in a high school class. They give it different names in different books. But the idea is you just take that, you plug it into there, and sometimes it's called like the plug-in formula for limits. And it's handy, but don't over-interpret this formula. This is not a formula you can just plug in. This requires not only that the function be continuous, but that you know that the function is continuous. You have to be able to argue why it is that you know in advance that this is continuous. Because otherwise you have a circularity problem. If you use continuity as an excuse to plug into this equation, and if you use that result as evidence that the function's continuous, then you have what we call circular reasoning, and that's not legitimate reasoning. Right? Is everybody comfortable with why circular reasoning is unacceptable? It's absolutely not okay. So the complaint would be, how can I use this to compute a limit if I have to know the function's continuous? In other words, if I have to compute a limit in order to justify using this formula. So what's the value in it? And the answer is that we have these theorems right here. These two theorems. Here's some free information. Thank you, old mathematicians from the 17 and 1800s. All polynomials are continuous. And you get to use that. No problem. Right? All exponentials are continuous. Now you got to cite it. You got to write that down. You got to say, because all polynomials are continuous, bam. Right? But it's been proved. You may cite this in Math 212, etc. A long list of other functions. And do be careful. It's tempting to say logs are continuous, and they are where they are defined. But logs are not defined everywhere. And so, of course, logs are not continuous where they aren't defined. That wouldn't make any sense. Likewise, trig functions. They're not continuous everywhere, but they are continuous everywhere they're defined. They are definitely undefined some places. In those places where they are undefined, they are wildly discontinuous. Wildly. Right? But where they're defined, they're continuous. And furthermore, roughly speaking, any way you can combine known continuous functions, the result is continuous. And so here's an example. Here's you want to compute that limit. It looks like a really hard problem. This is actually a really easy problem. The function on the right-hand side is nasty, but look what x is doing. X is approaching 3, 1. Everything in sight over here is barnyard variety familiar. All of these functions are known to be continuous where they're defined. They're all defined at the point in question. Right? The scariest thing maybe that happens is you're taking a log. Well, okay, you have log of 4. You're not taking log of 1. Right? You're taking log of 4. This is fine. No problem. Everything in sight's defined. The denominator is not 0. Fractions, you got to be careful with that one. By the way, fractions are not defined when the denominator is 0. So you got to make sure that you don't get 0. And as previously mentioned, we're not taking log of 1. So the log of 4 is not 0. It's some number. Who cares? And everything in sight's fine. This function is continuous. We plug in, we get an answer. So you don't have to check a bunch of paths. You don't have to do polar coordinates. Can you imagine? Can you imagine trying to deal with polar coordinates in here? It'd be a nightmare. Completely untractable. Right? Sight continuity. So, it's nice. Okay, that's a great stopping point. I again lost track of time, went a little bit over. Apologies. That's a good place to call it, and see y'all later. Oh, by the way, so today's Wednesday. The homework for Friday. Remember, homework's always due. Start a class on Fridays. We are now done through limits, and so all those exercises on the syllabus are assigned. I'll send out an email as soon as I get a moment back in my office. See y'all later.